All right, calculus. Sorry, the first part of this video is actually for Lydia. I thought about answering by Hangouts, but I don't know if I could answer it well that way. So, Lydia, I'm going to look at your questions and I'm going to answer what I can one by one. Number one, you said sometimes you wouldn't bother to find the intervals, but other times it seemed important. When do we have to find them? So when you have to find intercepts, which I think is what you mean, you wrote intervals, but I think you mean intercepts. Really, y-intercepts are always important because y-intercepts are very easy to find. You just make your x 0, plunk it in, and find it. The x-intercepts are when you make your y 0. If you have a linear equation where it's like x cubed or x to the 4th, that's going to be very complicated to find, so you don't need to bother. Any other time you really should. So again, if it's going to be really complicated, generally when you have a linear equation, so no asymptotes and things like that, but you have like an x cubed, like it's like 6x cubed minus 5x squared plus 9x minus 7, it's going to be difficult to find those x-intercepts and x-intercepts, so don't bother. That's what I would tell you. When you have asymptotes, it's generally easy to find the asymptotes. It's not really complicated math to do it, and you should. Question number 2. Do you care if we don't number the graphs and just count the squares on graph paper? Yes, I do. Here's why. Because on some of them, like if you graph 0 and 0 and you don't mark that, I don't care. But like one of our local maxes that we found was something like 3 and 324. Okay, you can't count 324 squares. You can't do that. Because it's a sketch and it's not always going to be one square for one unit, you can't just put it on a graph. You're going to have to label like where is your max, where is your min, because again, if you end up with a local maximum that is 3 and 324, you're not going to count 324 squares. You will have to label that. Number 3, I don't understand F when you start dividing the bottom out. I didn't understand why. I think you mean 4F. I think is what you mean. I didn't divide the bottom out in 4F. What I did in 4F, and again, I'm not sure, you just said F, so I'm not sure which F you're talking about. Were you talking about that F, or were you talking about 1F? I'm not really sure which F you're talking about. You divide the bottom into the top if there's an oblique asymptote. If the degree on the top is exactly one more than the degree on the bottom. So I'm assuming that you meant 1F because that's the one where there's an oblique asymptote. It was x squared over x minus 2. Because the degree on the top was one more than the degree on the bottom, that means there's an oblique asymptote, and you need to find the equation of that oblique asymptote. To find that, you have to divide the bottom into the top. It's the only way to do that. If you don't know how to divide the bottom into the top, I've explained it several times. Try Khan Academy, where it talks about dividing a binomial into a polynomial. See if maybe that helps a little bit. I'll see if I can find a video and attach it. Let me see. Number 4. I don't understand question 4. Sorry. And number 5, will questions like 4B be on the test? Did we do 4B? I don't remember doing 4B. We could have done 4B, I just don't remember it. Seriously, I don't remember doing 4B, but that's okay. Maybe we did. We didn't do 4B, so probably not, because we didn't do 4B. I don't know. So I hope I answered your questions. If you still have questions, let me know. Yeah, and I'll try and find a video on finding the equation of an oblique asymptote, and maybe they'll explain it a little better than I have. All right, so having answered those questions, we're moving on. And again, I don't know if I answered them adequately, but I answered them to the best of my ability. We are going into the word problems sections. There are 2 of them. We're moving into what is called optimization problems. Optimization problems is really all about finding maximums and minimums, because if I want to build something and I want to, so I made 2 raised garden beds for myself, and it came with these plastic panels, and you can make them any shape you want, but I want to maximize the amount of area that I have in my garden. What shape do I make it in order to maximize the amount of area? That's an optimization problem. I want to get the optimum use out of these gardens that I made. Maybe you want to minimize something. If you're talking about business, you might want to minimize the cost of something. That is optimizing your business, right? It's making it work optimally for you. And to do that, you want to minimize costs. So you would be looking for a minimum. So optimization problems are really all about finding maximums and minimums. And it really will depend on the question, but it won't matter, because when you find the answer, it will be the optimum answer. So you won't really have to worry too much. So section 6.7 is optimization problems in terms of things like area and volume. And then section 6.8 is going to go into business, so things like revenue and cost and those types, and profit and those types of things. So we're headed into section 6.7. I have that we're going to do 3 examples. And again, the questions I'm going to give you are mostly going to relate to rectangles. However, we're going to do one together that has to do with a cylinder. But I wouldn't give you one of those to do on your own, because I don't expect you to know, for instance, what is the volume formula for a cylinder. I don't expect that you know that right offhand. So, example number 1. We're going to talk about a very exciting topic, a cereal box. All right, we're going to talk about a cereal box. And a cereal box is in the shape of a rectangular prism. It needs to have a capacity or a volume of 5,000 centimeters squared. So we want this to hold a volume of 5,000 centimeters cubic centimeters of cereal. That's how much cereal we want it to hold. The thickness of the box needs to be 10 centimeters. And the reason why they say 10 centimeters is when you're grabbing the box off the shelf, that's a nice, easy thickness for you to be grabbing. If you've ever bought those big giant boxes at the Costco, they're great because they're cheaper. But you can't just pull those off the shelf because it's too big for most people's hands unless you have big man hands or something. And so 10 centimeters is really what they're looking for in terms of the thickness of the box so that it's easy to grab on and off the shelf. All right, so if we have a cereal box, and I can't draw very well, but if we have a cereal box, we have that the width of it, where you grab it, is going to be 10 centimeters. And I don't know, maybe it's Rice Krispies. Ooh, now I want Rice Krispie squares. If this quarantine keeps up, you're gonna have to roll me out of this house because all I've been doing is eating. And they call this the width of the box, and this is the height of the box. All right? Now, what dimensions of the box require the minimum amount of material? So when they're making these cereal boxes, right, they have to get the cardboard from somewhere. They want to minimize the amount of cardboard they need to make these boxes because that's less materials, therefore it's cheaper. So they want to know what dimensions. We know this dimension has to be 10 centimeters, but what should be the height and the width of the box in order to use the least amount of cardboard to make the box? All right. So we need to talk a little bit about how we go about these optimization problems. In optimization problems, you should be able to come up with two different equations. All right, so first off, they told us at the very beginning the volume should be 5,000 cubic centimeters. The amount of Rice Krispies I should be able to fit inside the box is 5,000 centimeters cubed. That is a volume. So volume for a rectangular prism is length times width times height. I do expect that you know that or are able to figure that out because you should have been learning that for several years now. We've done it several years in a row at our school, and other schools do it as well. So if volume is equal to length times width times height, and I know that my volume should be 5,000 centimeters cubed, I don't know what my length should be, I don't know what my width should be, but I do know that my height should be 10. Now, what am I trying to minimize? I'm trying to minimize the amount of cardboard that I'm going to need to make this box. That isn't volume. That is surface area. I need to make all the surfaces. I need to make the front and the back and the sides and the top and the bottom. I need to have cardboard on each of those sides. That's actually surface area. So surface area would be, well, one surface would be the front of this box, which would be height times width. But the front of the box and the back of the box are the same, so there are two surfaces that are height times width, plus this rectangle on this side is 10 by the height. An area of a rectangle is length times width, or, you know, the side times the side. So 10 times height. But again, there are two sides. There's this end, and then there's like, again, bad drawing. But then there's this rectangle on this side. So it would be 2 times 10 times height. And then there is the bottom. The bottom is the width times 10. But again, the bottom and the top would be the same size, so I would do 2 times 10 times W. Now I filled everything I can in here, and I filled in everything I can here. Now I can simplify this a little bit. I can go surface area is 2 times HW plus 20 times H plus 20 times W. Now, of these two equations, I want to minimize one of them. The one I want to minimize is surface area because I want to minimize the amount of material that I'm using. That's surface area. To minimize something, to find a local minimum, to put it in the language of the last section, to find a local minimum, we have to find the first derivative. The problem with finding the first derivative is if I try and find the derivative of the surface area, the problem is I have two different letters over here. I have an H and I have a W. That's going to be very difficult to find the derivative of. That's why we have this seemingly random information over here. What I can do with this seemingly random information is I can divide this side by 10, so I can divide this side by 10, so I have 500 is equal to length times W. And then what I can do is I can actually isolate one of those letters. It honestly doesn't matter which one you choose. The only reason why I'm choosing this specific one is I'm trying to choose the same one the textbook does, so that if you're looking at the textbook, what I did and what they did matches. So they isolated their W. What I mean by that is they divided this side by L, so they divided this side by L, so they had 500 over L is equal to W. Now, why would I bother to do that with this information over here? If W is 500 over L, then anytime I have a W over here, okay, if I have, I don't know why they're using, sorry, it shouldn't be L, it should be, I replaced the wrong letter, sorry, I replaced the wrong letter. This should be 10, and this should be height. And so this should be height times W. So I would divide by height. Sorry, my apologies. I just used the wrong letter so that it didn't match over here. All right, so if I now have W, it's not 500 over L, it's 500 over H. I just used the wrong letter. The logic is all the same. What should happen is over here, anytime I have a W, I'm going to replace it with 500 over H because W is 500 over H. So I have 2H, but instead of putting W, I'm going to put 500 over H plus 20. Now, H I don't replace with anything, I just leave it as H, plus 20 times 500 over H. Because I'm replacing W with 500 over H. Now I'm going to erase this over here. So I'm going to simplify this side a little bit. Here in this piece, my H's would cancel and I would have 2 times 500, which is 1,000. And here I would have plus 20H. And here I would have 20 times 500, which would be what, like 10,000? And, or is it 1,000? No, it would be 10,000. So it would be 10,000 and it would be over H. But instead of writing it as 10,000 over H, I don't really want any fractions in this, so I'm going to write H to the -1 and just bring it up to the top. Okay? So far all I did was I came up with my surface area formula. I used my volume formula so that I could replace one of these variables so that I only had one single letter unknown in my formula. So surface area is equal to 1,000 plus 20H plus 10,000 H to the -1. What I can do now, remember I am trying to minimize the amount of material used to make this. If I want to minimize something or maximize something, really what I'm looking for is a local maximum or a local minimum. In this case, I want to minimize something, so I'm looking for a local minimum. In order to do that, I have to find the derivative. The derivative of 1,000 is nothing. The derivative of 20H is 20. the derivative of this, I'm going to bring the negative 1 down, so I have negative 10,000 h to the negative 2, because remember I subtract 1. So I have that the surface area, the derivative of the surface area is 20 minus 10,000 over h squared. Now what was the rule? What was the rule when I was trying to find a local maximum and local minimum? I found the derivative, and then what did I do with it? Make it equal to 0. So I'm going to make it equal to 0. So I'm going to move this over here, and I'm going to have 10,000 over h squared is equal to 20. So I'll multiply this side by h squared, so I'll multiply this side by h squared, running out of space again, so I'm going over here. And so those will cancel. I have 10,000 is equal to 20h squared. I'm going to divide both sides by 20, and I'm going to have h squared is 500. And so I'm going to say h is the square root of 500. Whoops, square root of 500, which is 22.4 centimeters. So what I have just found is I have found that if I want to minimize the amount, then the height should be 22.4 centimeters. Now, how do I know what my width should be? I already know that the thickness is 10, because they told us that. I just figured out that the height should be 22.4. How do I figure out what the W is? Well, back on the board earlier, I had something that said width is equal to 500 over height. I had that back when I had isolated my W. So if I want to know what my width should be, and I now know that my height should be 22.4, then my width should be 22.4. When you do 500 divided by 22.4, you get 22.4. To minimize the amount of material that you need, you actually need to make a square box. By the way, usually if you want to minimize material, if you want to maximize your area, a square is the way to do it. Even when it comes to building houses, if you build your house in a square shape, it actually works out to be cheaper. You get more square footage for less house. So like my house, I think is 32 feet by 32 feet. But by building it as a square, it actually maximizes the amount of interior space that you have based on those dimensions. If I change that, so if my house is 32 by 32, if I changed it so that it wasn't a square, but it still added up to the same thing, like the perimeter still added up to the same thing, but I made it a rectangle instead, I wouldn't get as much space on the inside of my house. A square is the cheapest thing to build. You need less material for the maximum amount of space. Just a little tidbit when you end up building your own house, if you ever do. All right, example 2, optimal radius of a can. So this is the one that I wouldn't actually get you to do on your own, because I wouldn't actually expect that you know what the volume of a cylinder is right off the top of your head. A box, yes, but not weird shapes. So determine the most economical shape of a can that has a capacity of 355 cubic centimeters. So 355 cubic centimeters, because it's cubic, that means we're talking volume. So the volume of this can is 355 cubic centimeters. And it says determine the most economical shape for a can, and a can is always a cylinder. So in other words, what should the dimensions be? So if I have a cylinder, when we're talking dimensions, we're talking about what should the radius be and what should the height be. Should it be a really tall, skinny cylinder? Should it be a short, fat cylinder? What is the most economical shape? In other words, what would make it so that I use the minimum amount of materials to build it? I want the minimum amount of materials because it's cheaper that way. Again, building my house in a square meant I needed less material for the maximum amount of space. So the capacity in cubic centimeters of a cylinder can, a cylinder, the volume formula is pi r squared h. And again, that's not something I expect that you would just know off the top of your head. And so our volume is going to be 355, and that is pi r squared h. Now, what we want to minimize is the surface area, because we want to minimize the amount of material that I use. Whatever you want to minimize or maximize, depending on the question, that is what you're going to end up taking the derivative of. I'm not looking to maximize or minimize my volume, so I won't be taking the derivative of that formula. I want to minimize my surface area. That's the formula I'm going to be taking the derivative of. Now, surface area of a cylinder, again, not something I expect you know off the top of your head. It is 2 pi r h plus 2 pi r squared. That's actually the formula. All right. Now, don't think of pi as a variable. A lot of people get tripped up on that. They look at pi and think of that as a letter, but it's not. Pi is a constant. It's 3.14 whatever, right? So that's actually a number. Don't think of it as a variable. All right, so even though pi is not a variable, I still have two different variables in this question because I have an r and I have an h. Can't really do a derivative easily with two variables in it. We can if you just have an x and a y. We can do implicit differentiation, but technically we have three because we have surface area, we have r, and we have h, and we just can't do that. So we need to get rid of one of these variables. Again, that's why we have this seemingly pointless information here. Over here, what we're going to do is we're going to isolate one of the variables, either r or h. Now I'm going to isolate h. There isn't one that's right or wrong, but there is one that's definitely easier in this case. Because the r is squared, if I try and isolate that r, I'm going to have to take the square root of a whole bunch of stuff, and that's not going to be fun. So rather than isolate the thing that is squared, I'm going to isolate the thing that's not squared. Because to do that, all I have to do is divide this side by pi r squared, which means I divide this side by pi r squared. So h is 355 over pi r squared. So what I'm going to do now is I'm going to substitute that information into here. So my surface area, and I'm going to drop the s, I'm just going to put a for area. The area is 2 pi r, but instead of putting h, I'm going to put 355 over pi r squared. I don't know why I put a bracket there. Plus 2 pi r squared. Now I'm going to simplify that before I try and take the derivative. This pi will actually cancel that pi because I have one on top and one on the bottom. This r will actually cancel one of these r's. And I have 2 times 355, which is going to be 710 over r plus 2 pi r squared. Now again, I don't like that there's a fraction there, so I'm just going to write it as 710 r to the negative 1 plus 2 pi r squared. Now again, I'm trying to minimize my area. To minimize or maximize something, to find a local max or a local min, we have to find the derivative of this. So I'm going to find the derivative of this formula. So I'm going to bring the negative 1 down, which gives me negative 710, and I'm going to subtract 1 here, which gives me r to the negative 2. Now, please keep in mind that this pi is not a variable, but I also don't have to replace it with 3.14 whatever. When I bring this 2 down, I'm just going to multiply it with the 2 that's there, and now I have 4 pi r. Just leave it as in terms of pi. So again, this would be negative 710 over r squared plus 4 pi r. Now I'm going to make this equal to 0, and I'm going to solve. If I'm going to do that, okay, if I'm going to do that, just a sec. Okay, so, oh, I did the derivative. Oh, right, I'm making it equal to 0, sorry. If I'm going to make this equal to 0, if I bring this over here, I don't know why I just lost my brain for a second, over r squared plus 4 pi r. And that's equal, wait a second, sorry. I just brought that over there, left this on this side. I don't know where I was. All right, so I'm going to multiply this side by r squared so that they cancel. So I'm going to multiply this side by r squared. I'm just going to head over here. So I have 710 is equal to 4 pi r cubed, because I have r times r squared, which gives me r cubed. I'm going to divide this side by 4 pi. I'm going to divide this side by 4 pi so that I have 4 pi is gone. So I have r cubed is equal to 710 divided by 4 pi. So I'm going to take the cube root of this side. So I'm going to take the cube root of this side. Turns out that your r should be 3.84 according to the textbook, and I will even double check because I did it slightly differently than the textbook. I didn't, but I showed my steps a little weird, a little differently than they did. I didn't do it weird, I just did it differently than they did. 710 divided by 4 pi, and then the cube root of that. Ooh, I did not get that answer. Hold on. I did not get 3.84. Let's find out why. 710 divided by 4 pi. Oh, I think I did it wrong the first time. So the cube root of my answer, there we go, 3.84. Yeah, I'll tell you what I did the first time, just in case you happen to have a Harriet equivalent. The first time when I put 710 divided by 4 pi in my calculator, I did not put brackets around the 4 pi. My calculator didn't like that. So I put the brackets. It was much, much happier. So I have that my r is 3.84. Again, back here, I said that my height is 355 divided by pi times r squared. So to figure out my height, I'm going to do 355 divided by pi times 3.84 squared. Watch your order of operations on that, but it turns out that the height should be 7.66. Okay, so it should be 7.66. So if you want to minimize the if you want to minimize the amount of material to make this can, your radius should be 3.84 centimeters. The height of your can should be 7.66 centimeters. Okay? All right, one last example. And then I'm done talking. And then you get to try some. And if you struggle with it, please know that's not uncommon. It very often takes a little bit for this to kind of kick in. So example number 3 talks about an oil spill. And they say the oil spill that's generally regarded as having caused the most serious ecological damage in the world occurred when the oil tanker, the Exxon Valdez, ran aground in 1989. I actually think since then there's been one that's worse, but anyway, over 40 million liters of oil contaminated the sea near Alaska. To contain the spill, what they actually do, because oil lays on the surface of the water and then the currents kind of take it everywhere. So what they actually do is they take like these big styrofoam logs basically, and they float them on the top of the water. What that does is it allows the water to go underneath them, but the oil sitting on top gets contained by these. Sometimes they just use wooden logs if that's all they have, because wood will float, but they very often will use stuff made of styrofoam now, because styrofoam doesn't break down in the water the way that wood would. That sounded weird. So to contain the oil spill, rectangular booms that have a cross link to provide stability are used. So what they're saying is if they just use a rectangle, and remember, like, it's not just a set rectangle. There are different lengths that are connected. And so at those connectors, it can kind of move. So if they don't have something to stabilize the rectangle, it'll just kind of fold in on itself and then you won't have anything. So they need something, a cross piece in the middle, to help keep the rectangle open and keep it from collapsing in on itself. All right, so the cross link joins the long sides and is parallel to the short sides. So they label the long sides X and they label the short sides W. Okay. Now, what is the minimum total length of boom required to enclose an oil spill covering 100,000 square meters of water? 100,000 square meters of water. That's actually an area, right? Because it's square meters. If it was cubed, we'd be talking volume, but we're not. We're actually talking area here. So the area of this space is length times width, so X times W. So my area, which is 100,000, is equal to X times W. I'm not trying to minimize the area in this case. The area is staying 100,000 square meters. That is the constant thing that I want to enclose. What is variable is how long do I make this side? How wide do I make this side? That's perimeter. Okay, that's perimeter. If I want to maximize my area by using the least, or if I want to have my dogs have a certain amount of space in the backyard, but I only have, a certain amount of fencing, I need to minimize my perimeter, right? I only have a certain amount of boom, so I need to minimize my perimeter. So the perimeter, the amount of material that I need to make this shape, okay, they don't call it perimeter, they actually call it length, because it's the length of all the pieces added together. I'm going to call it perimeter. I don't care what you call it, all right? But I'm going to call it perimeter. and I have to have enough to go across. I have to have a piece that goes across here, and I have to have the same length of piece that goes across here. So I have to have two X's, plus I have to have a width here, a width here, and a width here, and they all have to be the same, right? So I have to have 3 widths in this case. It's helpful to draw a diagram so you can kind of see it a little bit. And this, I don't have any numbers for. For the area I did, but for this I don't have any numbers. This is what I'm trying to minimize. I'm trying to minimize the amount of stuff I need to put into the water to contain 100,000 square meters. So I'm trying to minimize this. So this is what I'm going to take the derivative of. But again, I've got 1, 2, 3 unknowns. Can't do that. So I have to isolate one of my variables. I'm going to isolate it up here. Now, I'm going to stick with what they're doing. They isolate the x. So they divide this side by w, they divide this side by w. It would be fine to do it the other way. Divide this side by x, divide this side by x, and isolate your w. It wouldn't matter. So in this case, x is 100,000 over w. So I'm going to substitute that into here. Perimeter is 2, but instead of putting x, I'm going to put 100,000 over w plus 3w. So that all I have on this side are just w's. I would even probably work that out because I'm like that. So this would be 200,000 w to the negative 1 plus 3w. I would probably do that. You don't have to. I probably would though. And so remember, this is what I'm trying to minimize. So I need to take the derivative of this side. So if I take the derivative of this, I'm going to bring the negative 1 down in front. So I'm going to have negative 200,000. I'm going to subtract 1 here. So I'm going to have w to the negative 2. I'm going to take the derivative of 3w, which is going to be just 3. I need to erase this because I need space. So now I'm going to make this equal to 0. So 0 is equal to negative 200,000. I'm going to move this back down to over w squared plus 3. So I'm going to take this whole thing, I'm going to move it over here, and I'm going to have 200,000 over w squared is equal to 3. I'm going to multiply both sides by w squared, so I have 200,000 is equal to 3w squared. I'm going to divide this side by 3. I'm going to divide this side by 3. So I just have w squared is equal to 200,000 over 3. And I'm going to take the square root. I'm going to take the square root of this side. I'm going to take the square root of this side. So I'm going to go to my calculator. And I'm going to do 200,000 divided by 3. And I'm going to take the square root of that. And I get that w should be 258.2. So back in that diagram that I had, where I had a w and a w and a w, this should be 258.2 meters, this should be 258.2 meters, and this should be 258.2 meters. Now I need to know what those lengths should be, so I would go back here and do 100,000 divided by 258.2, and so 100,000 divided by my answer, and I get that my x should be 387.3. Now in this case, a square is not the most economical, and that's because instead of just a length and a width, you actually had 3 widths, which throws things off a little bit. All right, there's one more example, but I don't bother to do it because it's really complicated, so I don't bother to do that. I'm going to give you some to try, and just give it your best shot. I want you to try it first before I sit and go through it with you. You only learn it by actually trying it, so I want you to try it first. So don't give it a good honest try before you tell me you can't do it, okay? But I do understand that the first time through this can be difficult, all right? So, but give it a try. Really try and read it and get a good picture of what's going on in the question, okay? Draw diagrams like I did if you have to. Those are the tips that I can give you. And then you should, again, always have two formulas. In this case, we had an area formula and a perimeter formula, one of which you need to take the derivative of. The other one you use to isolate a variable. Always the same pattern, but you have to decide, what am I taking the derivative of? What am I isolating with? All right? So give them a try, see what you can do with that. All right? And I will talk to you again tomorrow.